Today we are learning about signals and system. It is used by engineers to describe and process information. We'll go step by step, intuition first, and then we'll go to the math. A signal is just any information that varies. If something changes with time or space, that's a signal. For example, your heartbeat. If it's changing with time, that's a signal. The brightness of your TV, these are the pixels. So these are also signal in space. So basically, if it varies, it's a signal. For example, if you take x of t, it's a continuous time signal because the t is continuous. It can be 1.2, 1.234, it goes on and on. And that's why we're gonna get like a continuous signal from it. But if we have x of n is discrete, like 0, 1, 2. That's why this will be a discrete signal. Um, and then we have a system. System is very simple. Is you can imagine like your ear as a system. The sound that goes in, your brain processes the sound. Um, then imagine a filter. You can put noisy music as input, and then you get clean music as output. So basically, it will be, um, for example, y of t is the output, um, and then you get the system that is multiplied with the input. So x of t is the input, then you have the system, and you have the output y of t. Now we have to look into the continuous and discrete time signal. It's also very simple. The pink line that you are seeing here, which I'm highlighting with green, is a continuous time signal, like recording a singer voice with a perfect microphone that can hear like microsecond, can give you a continuous signal. But if you use your phone that has less samples per second to record the voice, you will get like sound that's not very continuous. It will be a bit discrete. So discrete is like we only measure certain points, um like pixel in the screen, and the sound wave is the continuous signal. And now let's move to analog and digital signal. Analog is anything that can take take any values, um like temperature rising and falling, and digital is only the signals that can take fixed values, like the computer can take 0, 1, and 2. So analog, x of t is like all the real numbers, but the digital is only x of n. It goes from 0 to 1 to and then infinity. Now the most interesting topic here is like understanding causal, non-causal, and anti-causal. It's a very simple topic. Causal is one that depends on present or past. For example, the light bulb is only glowing um when you are switching on the uh, like you're flipping the switch. So it's very realistic and it's happening in real time. Just the time you just flip the switch, it lights up. But so this is a causal signal. And then if you think of something that depends on the future, it will be a non-causal. For example, the Google Map estimate time of arrival, it predicts the future traffic. So it's a non-causal system. And then Anticausal is like something that depends. Um, it's like it's purely like physical. So imagine like it exists before the time starts. So imagine like you are on a mountain and you just like screamed, and then you can before like you can hear you can hear the echo of the voice, like also like hearing echo before you clap. So that's the type of system that is like anti-causal. Then there are a few things that we need to know before we do any signals and system um application or projects. One is time shift. So it's only like sliding left or right. So imagine you are playing a song and the song is delayed, so it will be a right shift. So for that case, if you have a system, um, that's if you have a signals and system like this one, you for the t, if the t is greater than 0, that will cause a delay, and it's on the right. But if you have like the song is starting early, then that's a left shift. So in that case, t is less than 0, and it's like advance left. Then we have time scaling. I mean, from the name, you can imagine what it will be. It's just multiplying the signal. So if you have a 2x speed, that's a compressed signal. And then if you have a less slower speed, that is going to be a stretch signal. This is only for like understanding, nothing related to any math. I'm just like putting this for example. So if um, the A is like is greater than 1, it will be faster, the music will be faster. If the A, like the scaling factor, is less than 1, it will be slower because you are reducing the speed. And if it's less than 0, it will flip in time. Then there is another one, it's called time reversal. So you are going backwards. That's why it's reversal from the name. For example, y of t is equal to x of negative t. And then you can combine all this idea together, which is combined transformation. For example, y of t is equal to x of negative 2t plus 6. Here, this negative is flipping. Then we have 2, like the factor, but it's negative, that's why compressed by the factor 2. Factor 2. Then we have a shift. So the 6 is, if you can take like common factor out of here, you see that it's 3. Then it's shift right because it's positive, shift right by 3. So if you're taking a voice note in the class, you can speed it up, you can reverse it, and you can start it later. And then what we learned is all the simple concept of signals and system, but this information are important because signals are like information and the system processes the signal, and These signals can be continuous, discrete, analog, digital, and causal, non-causal. And we can transform signals with this shift, scaling, reversal, and combination, which creates the foundation of communication and control system. And it is used in image and audio processing and pretty much everything, um, for communication and signals and system.